How we doing all? We doing all right? Cool. So we are re-exploring limits. We're going back through them to try to anchor out some of the details. In doing that, we're going to actually determine some truths and some insight about functions that we would not have recognized if we just allowed ourselves to stay with the simple definition, right? But again, this is a reminder. The entire class is built on tools that you have been playing with for years. So we are going to be building this all up from a place where you all have firm footing. So if I lose you at any point, just ask a question. Happy to go back through it. But all this has to make sense because today I'm going to introduce you to one of the first theorems of calculus. In other words, we're about to have a way of solving problems that is nothing but logic. Nothing but logic. There is no plug it in. There is no I got an answer. It's a complete discussion through something that is logical. It's weird. This will be one of the first times where you're able to do math where the math doesn't get you an answer. It just provides you with insight. And it's going to feel very weird because it's going to feel like the problem isn't done. But it's really not about trying to do the problem. It's about trying to understand what it's asking. And we're going to go through that. All right, so I've got a quote here, right, from C.S. Lewis. I thought I would bring in a literary reference. Mere change is not growth. Growth is the synthesis of change and continuity. Where there is no continuity, there is no growth. Let's again remind ourselves that like math is not about trying to give you all math terms for you to understand. It's for us to try to capture something you already know in a word. What does continuity mean to you all? When I say continuity, what do you think of? What does that mean?
Keep going.
To keep going? Okay, good. Anybody else? Let's build up some intuition. What do we know about what's continuity mean? Good. No stopping. Okay. No interruption. Right. Get that over for me if you could. Anybody else got anything else they want to add for that? So that means that in today's lecture, we're just going to do the logic of what happens if you are not interrupted. That's it. That's all we're going to do. But we're going to take that idea of something you already all have. We're just going to bring it into some math. We're just going to model it. We're just going to explore it. We're just going to challenge it. So that's going to be what we're playing with today, as we're playing with that idea. All right, so let's do a little bit of an intro here. You all tell me which one doesn't belong, and then give me a why. And how's you got an idea? Go ahead. The second, the top left? Top right? Okay. How come? They do what at the 2 points? What do you mean by discontinue? Oh, okay. So there's a place where there is no value. Like the graph does not exist above or below that. Is that what you're saying? At a single point, at a single x value. Mm-hmm. Okay, good. I'm going to change point to x value because point would just be a specific dot. Yeah, but at x values, at certain x values, there's no function above it or below, right? Somebody tell me visually, how would we describe this more artistically? Right? In other words, like how would we describe this to somebody with as few math words as possible? Like what looks different between the pictures? Like how do I rephrase what Minhas has, but I'm going to say I'm not going to use x value, right? That's mathy. Go ahead, Gail.
The graph to the top right is connected.
I like connected, right? Connected is good, right? We could talk about it as being something I could draw maybe without picking up my pencil, right? Now these are not excellent definitions because if I say I'm going to classify an entire group of equations based on if I can draw them without picking up my pencil, then that all of a sudden begs the question, what if I don't have a pencil? And then we have to say, oh, pencil or pen. And we say, well, what about if I don't have either of those? Does that mean I can't do math? right? Like we can start with intuition, but we don't land on that as a formal definition because then we've got to test everything by dragging a pencil across it. We need to instead describe what would prevent us from being able to drag a pencil across these. And then that way I don't have to rely on my pencil to do math, right? I rely on the story, the logic, the insight, what you are all seeing with your eyes. Okay, so we're gonna go from there. Good. So let's do a reminder here. When we're talking about limits, we have a very loose concept of the limit of the forever approaching, right? The logic of forever approach. We formalize that a little bit more by saying really what we're talking about is the ability to make a list of data. And for that list of data at some point to be able to be cut so that all the data after that point is as close to my claimed limit as I want it to be. That's the idea. In other words, it's squeezing in towards something, and after a certain point, all of the distances between my data and my limit are small enough. We're going to make that a lot more formal on tomorrow, but the challenge is that once I make it formal, it gets really, really intimidating. So we're going to introduce that to you all. We're not going to do too much with that formal definition, but what I want really is to just kind of develop within you all a comfort for what I'm talking about. A comfort for what I'm talking about is like asymptotes. How do I know there's an asymptote? Because at a certain point, I could cut the graph and say everything further is going to get closer, right? That's how I say that there's an asymptote there, because at a certain x value, everything past that gets closer to my asymptote. So for this one here, let's remind ourselves that sometimes the limit doesn't exist. Give me one time a limit does not exist. Give me a thing that I can break that causes a limit not to exist. Let's remember from last class. Good. If I can show that the idea of approaching doesn't always give me one agreed upon answer, right? I need one agreed upon answer. If I don't have one agreed upon answer, there is no limit because I can't squeeze in towards two things. I can only squeeze in towards one thing. Good. What's another? Be careful. I don't think that in limit logic we were ever trying to plug in, find that it didn't divide by 0 and then call it. I think every time we ever did that with limits, we tried plugging in with 0, realized that it wasn't going to work as a direct pursuit, so we instead had to explore the logic of approach, right? Find a different way of collecting data, find a different way of examining the function. So we got, it can't squeeze in towards two things. That's one way of breaking it. What's another? Yeah, exactly. If the act of squeezing doesn't even make sense, right? As x comes in, if there's no ability to squeeze down to a single point, then I can't claim that I have one point I've squeezed to. Like that would be an easy barrier, right? So I could have two, I could have an inability to squeeze. We've also got another where the function or the graph or the tendency just kind of runs off the paper, it blows up, right? Like if something just continues to grow, like what's the limit of x squared as x gets forever big? There's no limit, that thing's just skyrocketing. It's just gonna keep on going. So again, it all comes down to if I can make an argument that this data squeezes closer and closer to something, then we call that a limit. If I can't make that argument, there is no limit. Okay, that's really the idea. So let's play around with this one for an example. This is a challenging one because we can't hit this question directly. Let's remind ourselves again that if I do, I'll put it in brackets because it's going to be wrong. If I say that this limit is the same thing as just plugging in 0, what's the problem with that? That just tells me that it didn't work. That doesn't tell me that my logic was bad. The logic is bad here. What did I do that's against the logic? Yeah, the question asks about approach, and I started with at, right? I didn't do a single thing in the direction of what it was asking me for. I said, it's not there. They said, what did you get close to? I said, it's not there. And they said, but what did you get close to? See, we're missing each other because we're hitting a completely different conversation. It's like, did you expect there to be another stair walking down in the middle of the night? there wasn't a stair there. That's not what I was asking you. I was asking you, what did you expect, right? They're like, but it didn't happen. And I'm like, that's fine, but what did you expect, right? Like, for example, anybody here, if I asked you what you're gonna have for lunch, do we have plans? Anybody got plans for lunch? Kind of, sort of, right? What happens if your lunch plans don't happen? Does that mean that you were wrong for ever having plans? Like, it's fine to have plans, right? It's okay to say I was expecting something to happen and it didn't happen. But what we don't say is it didn't happen, so I never had plans. That would be illogical, right? It's okay to say I expected something and it didn't happen. Here, it didn't happen. This obviously doesn't have a value if I plug in 0, but it says nothing about the approach. So this is a good answer to a wrong question, right? Good answer to a different question. I'm asking about approach. So instead, let's go ahead and take a look at what this graph would be. This graph here, if you plugged in some data, we can imagine plugging in 2, for example. Absolute value of 2 over 2 will be 1. Absolute value of 3 over 3 will be, absolute value of a half over half will be, absolute value of 0 over 0 will be undefined. Good. Okay, so right, we got a little catch there. But for all those positive values, I had 1. So I can graph this by saying, above all my positive x values, I have a height of 1, 1, 1, 1, 1, 1, all the way on through. Great. What did I have above 0? An undefined. So there's nothing there. There is no value. What about negatives? Let's plug in some negatives. -1, absolute value of -1 over -1 would be -1. Absolute value of -2 over -2 would be, what was that again? -1, right? The denominator will be negative, top will be positive, so I will always have it be negative. So I end up having a bunch of -1, -1, -1, -1s for all those. So this becomes the graph. This is the graph of absolute value of x over x. So let's now ask ourselves, if I look at the logic of approach, I can approach x equals 0 by just kind of walking along this staircase. If I walk from the right, what do I expect my height to be? 1, because I was at 1, I'm on 1, I'm going to expect it will be 1. What about from the left? From the left, I've got -1, -1, -1. I think the height will be -1. So watch what we can do here. We need to show, like we now know from the graph, that the limit as x approaches 0 from the negative is equal to -1. And the limit as x approaches 0 from the positive is 1. The difficulty is that I don't want to have, I'm putting it again in brackets because this isn't a great solution. Because in order to justify this, I now have to get somebody to trust my graphing. I have to trust my eyes. And I have to get you all to trust my graphing and my eyes. That's not really a conversation of logic anymore. So instead, we want to force it through the algebra. Watch what we can do here. For the limit as x approaches 0 from the negative, actually, I'm going to start with this one over here. We'll work our way back. The limit as x approaches 0 from the positive. Let's again recall our data. If I was plugging in 2, I got what? How did that simplify? 1, because I got 2 over 2, right? If I plugged in 3, I got 3 over 3. If I plugged in 1/2, I got 1/2 over half, right? So for every single time, if I plugged in x for that conversation, I always got the same thing over itself, right? So I could say that this, for the purposes of only looking at it in the positive direction, is the same thing as is this true? Notice what I'm doing in my math here. I'm trying to force out the fact that I always got positive answer or positive input over positive input from that storyline. There's nothing that tells me I have to do this. This is me trying to explain what I recognized to the audience. But the advantage of that is, what is the absolute value of x over the absolute value of x? 1, so long as it's not 0, and we know it's not 0 because I'm approaching, right? So I'm not at. So I can say that this whole thing is the same as the limit as x approaches 0 of 1. Well, if I have 1, 1, 1, 1, 1, 1, 1, 1, 1, then the limit is 1. Again, what would tell us to do this? Nothing would tell us to do this. We are telling it what to do. We are trying to communicate through our math what we recognized from our logic and story and our exploration. Similarly over here, would it be fair for me to say, because I always got a positive thing on the top and I always got a negative thing on the bottom, which made it a -1 all the way across, I could make that appear in my math by saying, I'm going to make this like that. Isn't this true? And I'm not saying from an algebra standpoint. From an algebra standpoint, this is definitely not true. From an algebra standpoint, you can definitely not just introduce absolute value bars willy-nilly. But from a story standpoint, this is the same story. This is the same data. This would yield the same data. And it gives me an opportunity to show that from one direction, I always had -1. So if one direction I have -1 and the other direction I have +1, what is my limit? Remember, I'm looking for one thing that I can show all the data squeezes down towards. It's undefined. There is no single number that all of the data squeezes down towards. Because one set of data will never squeeze to anything but 1, and one set of data will never squeeze to anything but -1. So there's no squeezing that can occur here. There's no limit. So what we can say is we can begin to draw all of this much more concisely. Like, so what would a final answer look like that would communicate all of this? We can say, since the limit as x approaches 0 from the negative of absolute value of x over x gives us the exact same data as x approaches 0 from the negative of absolute value of x over absolute value of x made negative, which is equal to the limit as x approaches 0 from the negative of -1, which is -1, and the limit as x approaches 0 from the positive of the absolute value of x over x equals the limit as x approaches 0 from the positive of absolute value of x over absolute value of x equals limit as x approaches 0 from the positive of 1 equals 1. And 1 is not equal to -1, then since the limit as x approaches 0 from the negative of this thing does not equal the limit as x approaches 0 from the positive of this thing, then the limit overall does not exist. Notice the difference here between this and algebra. Did we plug things in? Sure. Did we use algebra? Sure. But what were we really trying to accomplish? What we were trying to accomplish was we were essentially trying to write an argumentative mini essay on if this is true, and if so, why or why not. Like, it's arguments. It's a model of logic. How do you want to model your logic? How do you want to communicate it? But it does eventually come to a place where we're not using single numbers, we're not using just pictures, and we're definitely not using data through the method of exhaustion. We are proving it through a story. Because this didn't rely on me having to draw anything. And yet I could still show this to somebody and they would not be able to argue with it. Go ahead.
So you
Say again.
so you would do the same logic.
Yes. So it's just that all the other limits that we've done in the class have all been easy so far. Like, for example, when I said like the limit as x approaches 2 of like x squared has no interruptions. Because it has no interruptions, what I'm trending towards is what I will actually get. Right? Here, what I was trending towards is different than what I actually got. So sometimes, if it's trending towards something unexpected, then we've got to go away from just plugging it in, obviously, because that wouldn't be what I'm trending towards. So we're trying to explore now, what do we do with the not nice functions? How do we explain that there are not nice functions and that those not nice functions don't have limits? We have to explain it through a sentence. We have to explain it through a story. Good. Any other questions on this? Continuity. Let's remind ourselves that like we are encountering these difficult problems because not all graphs are nice. And that's what we're going to try to pin down here. That just like we were just talking about, right? Like sometimes it's as easy as just plugging it in. Sometimes that doesn't work at all. How do we recognize when it's okay to plug it in and when it's not okay to plug it in? How do we categorize that so that we can organize our thoughts? So let's remind ourselves again. Let's take a look at this one. Would that graph be continuous? How come? Right? Help me pin down the language. Why? Why is that not continuous? Let's bounce it around to some other people who haven't participated with. What are we saying? Why is this not continuous? What was it? It makes a jump. Good. How did you see the jump? So you're looking right at where that jump is. Now here becomes the challenge. Visually, we see that. Mathematically, it's going to be very difficult to communicate that. Because what we've got to say is I looked at the nothing and the nothing there told me that there was a nothing there jump. Do you see how describing the holes is difficult from a logical standpoint, but it's exactly right from how we can recognize it visually. So we've got to find a way of getting at the idea that there was a jump without talking about the jump. Right? Because if you talk about the jump, there's nothing there. You can't talk about the nothing mathematically. Go ahead, Julia. Good. So we could say if there is nothing there, then I would be forced to have a gap. That's excellent. Good logic, right? So continuity has a part of it that says I have to be there. Good. But even if I did have something that was there, like maybe I put a point all the way up here, still wouldn't be continuous, right? So being there is one piece. What's the other piece? Like why didn't these connect? Because they approach different y values, right? So that becomes the second piece. That's all it is. Continuity can be broken into two pieces. I must actually have something there, and what I approach has to agree with what's actually there. And in that conversation, I'm not talking about the not there. I'm talking about things I can physically collect data on. What am I approaching? And is what I approach actually a connector? If that's true, then I must have connected. So watch how we can put that into a definition. Right? Let's double check it against some of these other scenarios just to make sure. In this one here, I am approaching, but I have nothing there. Is this continuous or no? Try it. Can you draw it without picking up your pencil? Some of you are saying yes, and I haven't seen your pencils move. Try drawing that without picking up your pencil. Nope, not at all, right? So this one is discontinuous. Why? Because it goes back to what Julia said. We're missing something there. If there's a gap, that will get in my way. Excellent. What about this one here? Here, I have an approach, and I don't have a gap, Like, at least not as far as there being an X value that doesn't have a height above it. It's just that I have a mismatch. I have a mismatch between what I'm approaching and what's actually defined. Okay, what about this one here? Here, again, I have something defined. I'm just approaching nowhere close. And over here, at every single moment, I have things defined. Right above 2, there is a Y value right here. But no matter what I approach, I never get an agreement where I approach that same thing, depending on all directions. So here's how we will capture all that in a beautiful, concise way. How do I prove if something is continuous without having to use my eyes? Because my eyes can be fooled. We've all seen plenty of optical illusions. Let's not say it looks continuous, so it is. That would be bad, right? That would be us doing bad science at best, right? Let's not say I see it, so it is. Let's say I logic it, so it is. If what I approach equals what is there, then I must always be connected. It's a wonderful moment where we are going to see the worlds of calculus and algebra collide. Because notice on the right-hand side here, this is algebra. It just says plug it in. It just says plug it in, tell me what you get. Plug it in, tell me what you get. That's algebra. That's calculus. That's the story of approach. I've got to consider patterns, data, trends, models, and then we say, does what I trend towards actually happen? If so, then that's a moment where I'm walking along the staircase. I expect there to be a stair, and there is a stair. Great, I don't stumble. Sometimes I expect there to be a stair, and there is a floor, or no stair, and I either fall through or I stumble. So sometimes we will have a nice continuous moment. Sometimes we will have a moment of interruption. And this is how we quantify that. Let me pause here for a moment because I really want you to take a moment and capture this in words that mean something to you in your notebook. Like you should be explaining it in your words and then working your way towards the formal. Does anybody have any questions about what this is or why I'm reading it this way? Good. Sure. So limit as x approaches a of f of x. Tell me what limits mean. It means we're talking approach. So this means approach as I get closer and closer to x being a. Good. So that means on the left-hand side, I'm talking about what do I expect to get, right? Right? As x gets closer and closer to a, like what's my data along it telling me I should expect? It says not a, but it does say y value above close to a, y value above close to a. What's my y values trending towards, right? And then on the right-hand side, that says plug in a, right? That says what is the actual height above a. So one says, what is my height trending towards? The other one says, what is my height? If my height that I'm trending towards matches the height that is, then I have no interruption. If what I trend towards is different than what I actually have, then what I trend towards is going to have an interruption against what's actually there. All right, we'll do some examples. But I got it, like I said, it starts from the story. So the story's got to make sense. The last chance. Do we have any other questions before we move on to examples? Don't rely on the examples to communicate the story. We approach the story with logic. Okay. So let's take a look at this one. Lots to graph here. If you want to graph it, go ahead. I'm kind of over it. Right? Could we graph it? Sure. The first thing is going to have some kind of an asymptote behavior. Maybe some stuff will cancel away. The bottom thing is just going to be a value. So as a story, this just says the top part has the potential for interruption. The bottom part has the potential to fill it. Let me pause here for a moment. Is anybody curious about where I'm pulling that storyline from before I even get into any of the heavy math? All right, the top thing has a chance of dividing by 0. The top thing also has a chance of maybe making a whole, maybe making an asymptote. The bottom thing says at x equals 1, my height is a half. So hopefully this matches and I get a nice steady flow between both of those models. Maybe they won't match. We're going to try to figure it out. Okay, so first things first. If I'm trying to figure out if it's continuous, it's best in math that whenever I give you a word that we have defined, we start with the definition. That way we know that we're answering the question directly and we haven't changed anything. So continuous means what? Who can remind me? Good, that's the idea of it, but that's not the definition. The definition was on the last slide. You want it good? Very good. There we go. That's the definition. If I can make that appear, then I am good. Notice, by the way, does it have the idea of drag my pencil and don't lift it up? Yes. But is my approach going to be, I try to draw this without picking up my pencil? No, because that's going to rely on me, my pencil, my artistic skills, no logic, right? So we're going to try to prove that I could draw this without picking up my pencil, but that is not the approach. So instead, what we're going to do is we're going to look at this moment by moment. Let's start with the algebra. The algebra is going to be the easiest part. The algebra says, what is the value at 1? Right? So we'll go ahead and frame this specifically to our problem. Let's make it, instead of plugging in A, we're going to plug in 1. So you all tell me, what is my height if I plug in 1? It's 1. Very good. If f of x equals 1/2 whenever x is 1. So if x is 1, my height is 1/2. Good. So we just start that off. F of 1 is 1/2. Great. Simple, straightforward, to the point. Let's take a look now over here at the calculus thing. The calculus thing says, not what do I approach, or sorry, not what do I get, because that's what algebra says. Algebra says, what do I get? Now let's compare this to what I approach. So first question, am I going to get something different if I approach from below or above? That's tough, right? That's tough. It's worth exploring. You have to explore it every single time. So let's first say, we're going to look at it from the positive and we're going to look at it from the negative. So if I plug in a little bit less than 1, that would be what? What's a good number? 0.98. Good. Let's plug that in. What are we going to get? Oh, we could get data. Data is going to be hard. We're just going to have to make a big table. That will be annoying. Watch this. We're going to plug in data to the top equation, right? So for this conversation, do I use the 1/2 at all? No, I'm using the top one. So watch what I'm going to do. For this conversation, I'm looking at x as it approaches 1 from below, but I'm going to be considering this for my data. We all agree? And then I could say, okay, is there a way I could make that a little bit easier before I start getting data from it? Sure. I can make this x minus 1, and I could factor the bottom so that it's x minus 1 and x plus 1. Do we all still feel good that that equation would get me the same data? Do we all agree that if I canceled away the x minus 1s, that that would also get me the same data? Not because it goes away, because I could have a divide by 0 error there, but because in the conversation, I never have the divide by 0 error. So for data collection nearby, it will get me the same data as just this one. Right? So long as I don't create a divide by 0 error, this function gets me the same data. And so now I can ask, as I get closer and closer to 1, what's this going to trend towards? 1/2, how come? Exactly right. We can imagine plugging in forever close to 1. Here, there's no barriers about actually getting 1, so the data is going to continuously trend towards 1/2. Notice, by the way, that this would be the exact same thing we would do for the other directional limit, right? Because we still would have used that exact same equation. And we still would have simplified it the same way because it would have gotten us the same data. We would just be considering it as I came from a little bigger. So now I'm talking about 2.1, 2.01, 2.001, 2. As I keep getting smaller, and X keeps getting, sorry, 1.1, 1.01, 1.001. As things start getting closer and closer to 1, this is going to trend towards 1/2. Good. So what we then do is we say, look, what I trended towards from the left and what I trended towards on the right matched what I actually got. My question to you all is this continuous? Well, the question is there an interruption? If there's not an interruption, isn't that what it means to be continuous? Right? If I'm trending, and I get that should be nice, easy stair-step transition, like nobody noticed. Like there was going to be a gap, and somebody just like held up their hand in the picture and just kind of carried somebody across that one moment. Right? That's what that point did. It filled the interruption. So we can now say with all of this supporting work, a nice little summary argument. Since the limit as x approaches 1 from the negative of f of x equals the limit as x approaches 1 from the positive of f of x, then I can say that the limit overall exists and is equal to 1/2. Also, since plugging in the value equals 1/2, which equaled what I got from my limit, f of x is continuous. Right? It's an explaining. It's a convincing argument. This is an entire chapter of convincing arguments. So you have to make the argument. You have to explain the thoughts. You have to go from what it means. You have to figure out a way of approach. But at the end of the day, what you're really trying to do is we're trying to say, I need to look at the approach. The approach has 2 directions, and you make sure that both of those directions agree on what I actually get. And then we just do it on repeat. All right, let's talk about this one. Now that we're getting a little bit more comfortable with this logic of approach, notice some of the powerful logical conclusions we can make from it. For example, here's a question. If I have a bathtub and I have it filled with warm water, and I slowly pour cold water into it until I reach my desired temperature, right? I'd like to give myself a little spa day. I work hard. I have no weekends. I'd like to have myself a nice warm bath, but it still starts off a little too hot. I pour some cold water in it until it gets to my preferred temperature. My question is, if it ends at, let's say, 7 or like 180, and it started at 212, was there a time that it hit 211, 210, 209? Right? Like, did it hit all the temperatures in between as it went from 212 down to 17? It gradually changes. If I was going to graph that, would the graph be continuous? Yeah, right? I would slowly be able to drag my pencil along its transition of temperature until it settled down on some final point. Now, you just did a logical conclusion. I didn't have to give you a single function. And if I asked you, when was it 184 degrees, what would you say? You have no idea, do you? And that's okay, right? It doesn't mean that this is not still a good logical conclusion, right? Math is a model of logic, not a model of plugging in things. Is it right? Because it's in that act, right? Like the only contrast, anybody here ever seen Spy Kids?
Yeah.
right? Like that's the only way that I could think that it might not, is you put like the thing in the microwave, you wait 5 seconds, and all of a sudden like Happy Meal just pops into existence. Like that's not usually, right? Slowly it builds up temperature, which is why I can interrupt the process at any point, and I would expect something in between. If I interrupted this process, by the way, and it was all of a sudden at 112, and then later it climbed back up in temperature, when all I've been doing is adding cold water, that would be weird, right? I introduced more cold water so it got warmer. That would be weird, right? You claim it, write some data, get a Nobel Prize. So like here, but we are talking about that steady decrease. This right here, this logic is what we call the intermediate value theorem. It's literally saying, if I start somewhere and I end somewhere, and I know that the change was gradual, I must have hit every value in between. It does not say when I hit that value, but that's okay. It just simply said, I did. Let's look at how we can apply that. I'm going to first try to write it with proper mathematical language. It's the exact same thing we just started with. So we're going to take this line by line, and we're going to make sense out of it. Because this is the intimidating part of theorems, is that we get intimidated by everything it says, and we forget that it came from a very easy, simple, makes sense to us story. So first, suppose that f is continuous on a closed interval a to b. Who can tell me what that means without math words? So it goes specifically across 2 points, that like has a domain. Specifically, I can draw it across the domain. Does it get interrupted?
No.
No, right? How would we prove it doesn't get interrupted? We've explored. I got to look at limits from left, from right, make sure that it always matches what I actually get. But at its essence, this is saying, if I have a slow transition story across 2 points in time, great, that's good. I can think of that. Then let n be any number between f of a and f of b, where a and b are not the same. Let's take a moment. Let's try to decode this. What does this mean? Give it a shot. Good. Some output, right? Some y value, some height. Sure. All those work. They're all good.
In the middle of our initial y value and end value.
Good, right? Where I started my story and where I ended my story. Like, for example, here, what is my n value? My n value is this, right? Some temperature in the in-between. So I started my bath. I finished adjusting my bath. Somewhere in that time interval, I would have hit this. When? Don't know. But this is in between the hottest and the coldest temperatures. Good. Then there exists a C in the open interval AB such that f of C equals n. So let's again pause. C is in AB. What does that mean? In between. So back in my story, what would that be? What would that? What parallel? It's not a temperature. C is not a temperature. It's a moment of time. Exactly right. It's a moment of time between my start and finish. It's a moment of time such that the height above that time is anything that's in the in-between. In other words, I could have chosen 180. I could have chosen 179. I could have chosen 183. And all of those would have had a time where that would have needed to happen. What time? No idea. But it would have needed to happen. So let me do a quick example here. I know it's going to take us a little over. Give me just a moment. Let's see how I can use that for problems like this, where I want to see if there is a solution to these equations. Does this thing ever have a solution? It'd be nice to know before we start plugging and chugging. In fact, this one's going to be very difficult to solve without a computer. But watch how I can show that it's not going to be a worthless effort. Let's consider, like, I don't know, maybe just a number. Let's try x equals -1. Then I can plug that in. What would that be? First thing would be -4, -6 would be -10, minus 3 would be negative 13. Negative 15, I think, comes out to negative 15. Let's try x equals 2. That'd be 8. 8 times 4 would be 32. Minus 24 would be 8. Plus 6 would be 14. Minus 2 would be 12. So you all tell me. If on the negative side, I was at negative 15, and on the positive side, I was at positive 12, was there a time that I crossed 0? If I'd have to be, because this is a gradual polynomial curvy type function, I'd have to hit it. So we can say, is there a root? Yes. By the intermediate value theorem, since f of negative 1 equals negative 15, and f of 2 equals 12, there is a c such that f of c equals 0. By the same logic you all had. All right, we've got next class details up on the board. We're going to be talking about how do we use reference functions as a way of determining limits if we can't use the function given exactly. And we're also going to start to pin down what does this forever approach mean? How do I prove that things squeeze in as close as you ever want? I'll give you the formal language next class. If you have any questions, feel free to stick around.